Niacin, long known for its lipid-lowering properties, is gaining recognition for its deeper, cell-level influence on cardiovascular health, especially its ability to mobilize cholesterol from lysosomes in macrophages, cells that play a central role in the development of atherosclerotic plaques. The research detailed in this study offers a compelling picture of niacin not just as a cholesterol-lowering agent, but as a molecular conductor orchestrating calcium signaling and cholesterol trafficking through a finely tuned network of cellular pathways. At the heart of this process is niacin's activation of CD38, an enzyme that catalyzes the formation of nicotinic acid adenine dinucleotide phosphate, NAP. NAP, in turn, triggers the release of calcium from lysosomes via TRPML1 channels. This calcium signal appears to serve as a molecular switch that upregulates liver X receptor alpha, LXRA, a transcription factor that drives the expression of key cholesterol transport proteins, Niemann-Pick type C1 and PC1, ABCA1 and ABCG1. This cascade of events leads to a remarkably efficient mechanism for clearing excess free cholesterol trapped in lysosomes. Macrophages challenged with oxidized LDL, a pathological hallmark of early atherosclerosis, often accumulate cholesterol in their lysosomes. This buildup is harmful, triggering inflammation, foam cell formation, and ultimately plaque development. However, niacin's stimulation of CD38 and subsequent calcium release through TRPML1 facilitates the exit of this trapped cholesterol via NPC1, directing it either for storage or for reverse cholesterol transport through ABCA1 and ABCG1. The result is a significant reduction in cholesterol-induced cellular stress and inflammation. Notably, this mechanism appears to function independently of systemic cholesterol levels. In animal models, niacin significantly reduced plaque formation without changing plasma total or free cholesterol. This strongly suggests that niacin's anti-atherosclerotic benefits may derive more from its ability to regulate intracellular cholesterol handling and immune cell function than from its effects on lipoproteins alone. The anti-inflammatory benefits of niacin also become clearer in this context. Free cholesterol accumulation in lysosomes can disrupt lysosomal membranes, prompting the release of cathepsins and formation of cholesterol crystals that activate inflammasomes. These inflammasomes, particularly NLRP3, stimulate the production of pro-inflammatory cytokines like IL-1S. Niacin, by promoting cholesterol efflux from lysosomes, prevents these stress signals from accumulating, reducing IL-1S production both in vivo and in cultured macrophages. Importantly, this anti-inflammatory effect was lost in CD38 deficient models, reinforcing the essential role of CD38 mediated calcium signaling in the protective actions of niacin. Moreover, niacin not only prevented inflammatory cytokine release, but also improved cell survival. Macrophages exposed to oxidized LDL undergo apoptosis and necrosis in response to lipid overload. Niacin-treated cells showed higher viability, suggesting that its effect on intracellular cholesterol trafficking also protects against cell death, another key contributor to plaque instability in atherosclerosis. Together, these findings cast niacin in a far more sophisticated light. Rather than acting solely by altering lipid levels in the bloodstream, niacin intervenes directly in macrophage biology, reprogramming cholesterol handling, suppressing inflammation, and preserving cellular integrity. The activation of TRPML1 calcium channels and LXRA signaling is central to this effect, positioning niacin as a unique pharmacological tool that bridges metabolic regulation and immune modulation. While further research is needed to fully elucidate the mechanisms by which niacin promotes CD38 expression and LXRA activation, these insights offer a new framework for thinking about niacin therapy. It is no longer just an old drug with modest effects on HDL. It is a potential modulator of intracellular lipid trafficking and immune homeostasis. This paradigm shift may explain why niacin, despite controversies over its utility in modern lipid management, continues to show promise in experimental settings where inflammation, cell stress, and lipid metabolism intersect. In summary, by harnessing lysosomal calcium signaling and activating key transporters via LXRA, niacin offers a multidimensional approach to combating atherosclerosis, one that reaches beyond traditional lipid profiles and into the fundamental biology of cholesterol management and immune regulation.